we're going to walk through the mechanism for the chlorination of benzene. And this mechanism will be the same for the bromination. You just change the Cl with the Br. And for these electrophilic aromatic substitution reactions, there's going to be two main parts to the mechanism. The first is to generate the active electrophile that will react with benzene. The second part is to do the actual electrophilic aromatic substitution. So for this reaction, let's start by generating the active electrophile. So that happens when Cl2 and iron trichloride are mixed. So here's the structure of Cl2, and let's draw in the lone pairs. And here's iron trichloride. I won't draw the lone pairs on those chlorines. So what's going to happen, iron is a Lewis acid that wants electrons, and chlorine just so happens to have lone pair electrons that it can donate. So what will happen is one of the lone pairs will add to the iron and give us a Lewis acid base adduct. Here's the new bond. I'll draw it in red for emphasis. Now the iron was neutral. It accepted electrons, so it now has a negative charge. The chlorine in the middle was neutral. It now has two bonds. It has a positive charge. This Lewis acid base adduct is now our active electrophile. And what it is, it's our electrophilic source of Cl+. Now, it's not quite as simple as just moving those electrons and getting Cl+. The benzene will end up reacting with this structure. So that's the second part of the mechanism, which is the electrophilic aromatic substitution. So now we'll have benzene. And I'm going to go ahead and draw in the hydrogen that we're going to end up getting rid of throughout the course of the reaction. So this will react with, we have our Cl, Cl, and I'm just going to abbreviate FeCl3. Now, from here, the benzene will act as a nucleophile. So let's highlight a bond in benzene. We're going to use these pi electrons here as the nucleophile. Now, a common mistake is for people to start here and draw their arrow to the Cl+. That's not correct. Even though that chlorine has a positive charge, it already has two bonds. Chlorine wants just one bond. Two bonds is pushing it. This would give the chlorine a third bond. That's not going to happen. What will happen instead is these pi electrons will attack this chlorine, which will in turn send those electrons over to the Cl+, making it neutral. So what do we get? We get our ring. We still have the hydrogen. I'll draw the new bond to the chlorine in blue because those are the pi electrons we used. Here's the Cl. We took electrons away from this carbon on the bottom, and we got a positive charge. Our other product is the Cl FeCl3-. From here, we have temporarily lost aromaticity. This structure that I've drawn with the carbocation is non-aromatic. It really wants to reform the aromatic ring for stability purposes. So what's going to happen next? The chlorine from this iron tetrachloride, it wants to lose that to give back the neutral iron. So that Cl, the electrons in this bond, those will come out of the iron over here to the hydrogen. We'll take the hydrogen from the ring, and then those electrons will fall down to give you the pi bond. So what we end up doing, we reform the aromatic ring. We've now generated the HCl. And we've regenerated our catalyst. So you'll remember at the start of the chapter that I said reactions are favored where aromaticity is retained from starting material to product. And in fact, the starting material is aromatic. The product is aromatic. Aromaticity is temporarily lost in the intermediate, but it's retained in going from the starting material to product, which is the most important thing.